The universe is vast beyond any human scale of comprehension. Billions of galaxies, each with billions of stars scattered across an ocean of darkness. It's a scale that inspires awe and a deep sense of loneliness. But its sheer size isn't the primary reason we might be alone. The real barriers are far more fundamental, woven into the very fabric of space-time. The universe imposes strict rules, an absolute speed limit, a constantly expanding canvas, and clocks that refuse to synchronize across vast distances. These aren't engineering challenges we can someday overcome. They are laws of physics. Tonight we explore why these laws make it profoundly, perhaps insurmountably, difficult for any two intelligent civilizations to ever meet. Let's keep it simple and honest. Our first and most famous constraint is the speed of light. Nothing, not a message, not a starship, not a single particle of information, can travel faster. 299,792 kilometers per second. It's a speed that could circle the Earth more than 7 times in a single second. It feels instantaneous, absolute. But that intuition shatters when you face the void between stars. The nearest star system, Proxima Centauri, is over 4 light-years away. A message sent today, traveling at the maximum possible speed, wouldn't arrive for more than 4 years. A reply would take another 4. An 8-year round trip for a simple hello, and that's our closest neighbor. The dark between stars is a gulf of time, not just distance. This speed limit creates a peculiar effect. When we look far away, we are literally looking back in time. The light from a galaxy 10 billion light-years away has been traveling for 10 billion years to reach our telescopes. We aren't seeing that galaxy as it is today. We are seeing it as it was 10 billion years ago. If a sophisticated civilization thrives there, we would have no way of knowing. We only see the light from their cosmic dawn, perhaps from a time before their star had even formed. Our most powerful telescopes are time machines that only look backward. Any message we send is a shot in the dark, aimed not at a civilization, but at the ghost of its ancient past. But the problem gets worse, because the stage itself is not static. Space is stretching. This isn't like galaxies flying through a fixed, empty void. Instead, the fabric of space-time itself is expanding, carrying galaxies along for the ride. The classic analogy is raisins in a rising loaf of bread. From the perspective of any single raisin, all the others appear to be moving away, and the farther away they are, the faster they recede. This is the Hubble expansion, and it means the gap between any 2 distant points in the universe is constantly growing. For decades, we wondered if this expansion might slow down, perhaps even reverse. But observations revealed the opposite, and something far more profound. The expansion is accelerating. A mysterious force we've labeled dark energy is pushing everything apart, faster and faster. This acceleration isn't just a curiosity, it fundamentally redraws our cosmic map. It creates a boundary in the mathematics of space-time, a cosmic event horizon. This is not a physical wall, but a point of no return. Any galaxy that crosses this horizon is receding from us faster than the speed of light. Light sent from there now, or from us to there, will be stretched into nothingness, never completing its journey. They are lost to us forever. This leads to a crucial distinction. The observable universe, everything whose ancient light has had time to reach us, is currently about 94 billion light-years in diameter. But the reachable universe, the collection of galaxies we could ever hope to exchange a signal with, even in theory, is far smaller, only about a third of that size. We can see the ghosts of galaxies we can never, ever talk to. Every second, more galaxies slip over that horizon, their light redshifting into oblivion, their futures forever disconnected from our own. Now let's zoom all the way back in, to our own tiny corner of the cosmos. For about a century, we've been leaking our existence into space through radio waves. This creates a radio bubble, expanding around Earth at the speed of light. But this bubble is only about 200 light-years across, a minuscule drop in the 100,000 light-year expanse of our own Milky Way galaxy. And these signals are incredibly faint. They weaken with distance, following the inverse square law. quickly becoming indistinguishable from the cacophony of cosmic background radiation. Our whisper of existence is almost immediately lost in a cosmic storm. So, instead of a passive bubble, what if we actively try to make contact? Suppose we build a powerful transmitter and aim a focused beam of energy at a promising star. The first question is, which one? There are hundreds of billions of stars in our galaxy alone. Do we target the nearest? The most sun-like? For how long do we transmit before moving to the next target? 1,000 years? 1,000,000? If our aim is off by the tiniest fraction of a degree, over interstellar distances, our beam will miss its target by light years. It's a needle in a galaxy problem, where the haystack is not only moving, but also expanding. If messages are too slow and uncertain, what about sending ships? This is where the physics becomes even more unforgiving. Accelerating a vessel to a significant fraction of light speed requires energies that dwarf our entire global energy consumption. And even if we could, the journey is perilous. At near light speeds, a stray grain of interstellar dust, no bigger than a speck of sand, impacts with the explosive force of a bomb. A robust shield would be necessary, but the constant bombardment would be like flying through a continuous hailstorm of micro-artillery. Surviving a trip to even the nearest stars would be an epic feat, and the timescales are immense. Trips would last not for years, but for decades, centuries, or millennia. You don't just cross a continent here, you cross entire historical eras. Einstein's theory of relativity adds a final, cruel irony. As your ship approaches the speed of light, your personal clock slows down relative to the universe you left behind. This is time dilation. It feels helpful. You could travel for what feels like a few years, while centuries pass on Earth. But this same effect works against you. While you age less, the universe outside your ship continues to expand at its relentless pace. Your destination, which was already fantastically far, is now even farther away. You might arrive at your target star system only to find that the home you intended to report back to has now drifted beyond the cosmic event horizon, making a round-trip conversation impossible. You become a permanent exile in time. In the very long run, gravity manages to win a few local battles against this cosmic expansion. Our own Milky Way, the Andromeda Galaxy, and a few dozen smaller dwarf galaxies are gravitationally bound together into what we call the local group. We are on a collision course with Andromeda, destined to merge in a few billion years. This cluster will remain our cosmic island home, but beyond it, almost everything else is being carried away by the accelerating expansion. We will watch as distant galaxies redshift away, growing dimmer, redder, until their light fades completely, leaving us in an immense, intergalactic void. The ocean of dark energy keeps rising, and the shores of other galactic islands are receding forever. Let's run a final thought experiment. Imagine two advanced civilizations emerge in galaxies far from each other. Both are curious, both are capable. They detect the faint, ancient light of each other's homeworlds. They both decide to act. One sends a powerful message. The other launches its fastest possible starship. They both try, with all their technological might, to bridge the gap, but the grid of space-time expands beneath them. The light from the message stretches, its energy draining away. The starship fights against the current of expanding space, a journey that gets longer with every passing moment. The red arrows on the cosmic map, representing their efforts, never meet. In the end, their immense effort can't outrun the fundamental geometry of the cosmos. So perhaps the great silence, the eerie lack of any evidence for extraterrestrial intelligence, isn't a sign of absence. It's not necessarily that we are alone. Maybe it's a sign of insurmountable separation. A universe where space is too stretched, time is too offset, and signals are too faint to ever cross the chasm. A quiet, empty-looking void can hide a crowded, lonely history of civilizations that lived and died, forever isolated on their own cosmic islands. This cosmic forecast seems bleak, but it also brings clarity. It tells us where to look. If contact is ever to be made, it won't be with beings from another galaxy. The possibility that remains lives close to home, right here, in our own Milky Way. Within a few tens of thousands of light years, the expansion of space is negligible, overcome by the galaxy's own gravity. Here, the only barriers are the speed of light and the vast but not infinite distances. We are looking for neighbors, not intergalactic pen pals. And that is precisely why we still listen. It's why we build vast arrays of radio telescopes. Their dishes turn to the sky and launch powerful infrared eyes like the James Webb Space Telescope. We conduct patient, methodical surveys of nearby stars, searching for the faintest technosignatures. The odds of success may be infinitesimally small, but the potential payoff is nothing less than cosmic. It would redefine our place in the universe. And even a continued silence is a meaningful result. It helps us map the boundaries of our own solitude and appreciate the preciousness of our own world. Soft. We may not be alone in principle, only alone in practice, separated by the unyielding laws of physics. And so, we light our nearby dark. We care for our own fragile island in this immense cosmic ocean, and we continue to send our careful, hopeful whispers to the stars. Because someone close, someday, might just whisper back.